We move on from the concept of resonance and we now talk about power. So for power, we learned about it in chapter 3 on DC circuits that P is either equals to VI, or is equals to V squared over R, or is equals to I squared R. So these three equations here are equivalent and you can transform from one form to another form, okay, just using Ohm's law. Okay, so in chapter 3, DC circuit, we know that the voltage across any circuit component will be constant with time. The current flowing through any circuit component will also be constant with time. Okay, different branches can have different current, but as time passes, the current and the voltage should be constant. So if V is constant, I is constant, I suppose you can assume that the P, the power that you obtain, will be constant as well. So resistance also the same thing. Resistance, if you are not changing a temperature, you are not changing a resistivity, the length, the cross-sectional area, should have constant resistance as well. So in DC, you always expect the power to be constant with time. It is not changing with time. Now we move on back to chapter 6. Chapter 6 is on AC circuit. So we are expecting the current and the voltage to be oscillating with time. If that's the case, I suppose you can deduce that the power that we obtain will also be oscillating as time passes. Okay, so in that case, dealing with power in AC circuit, we cannot just give you a value because this value is actually changing with time. So what can we do is we can represent it with a few different ways. The first kind of power that you can obtain is the instantaneous power. I've written it here, instantaneous power. So instantaneous power is a power at a specific moment. Let's say I want the power at time equals to 5 seconds. Then probably if you sub in everything, then you can get the power. So that's the power at that specific moment. Okay, so if it's a resistor, it can be the power dissipated in the resistor at time equals to 5 seconds. If it's a power supply, power supplied by the voltage supply at time equals to 5 seconds. Okay, it depends on what's the circuit components. So the first method is, the first thing you can find is the instantaneous power. The second thing that you can find is the average power. If you are talking about average power, we are not specifying any kind of moment. We are not specifying a time. We are asking that if our power is oscillating like this, then what is the average power dissipated in that circuit component, or the average power supplied by that component. Okay, so for different kind of circuits, you have different average power. Okay, we'll be talking about average power here, and for different kind of circuits, pure R or pure C or pure L, you see that the average power will be different. So let's try and figure out the equation for power. Then after that, we use a graph to average things to become average power. So let's look at pure R circuit. For pure R circuit, you have to multiply the oscillating V for across the resistor and the oscillating I across the resistor. Okay, so you know that they are both in phase. So you see that for V, it's V naught sine omega t. For I, is I naught sine omega t. Both of them share the same phase. So if you multiply these two things together, you get the equation which is V naught I naught sine square omega t. Okay, you can use any graphing calculator or can use what you have learned from your maths to draw this graph over here. So if I draw this graph over here, the blue color is representing the current, and as you can see, it's a sine curve. V, which is the red curve, is also a sine curve. So if both of them are sine curve, the peak and the trough for the V and the I should be aligned. Okay, so in this case, we call it in phase. And we know that this power here that we obtain is actually just a multiplication between the red curve and the blue curve. So you see that for peak, you multiply with peak, then of course it will be a larger peak. For trough, it's negative value, multiply by another trough, which is also a negative value. So if negative times negative, you should get a positive big value as well. So as you can see, the trough in the V and the I will translate to another peak in the powers curve. Okay, so that's for peak and trough. How about the point where it's equals to 0? At this point, which V and I is equal to 0, you know that V times I will be 0 times 0. So therefore, it will definitely be a 0 for P. Okay, so you can see that the power curve here will have peak at all the points where V and I are peak and trough. V and I, if they are peak or trough, then it will translate to a peak in your power curve. Whereas points where V and I is equal to 0 will translate to a trough in your power curve. So I hope you notice that before this, our period is for this long. Our period is from time equals 0 until this point over here. But once you translate it to the power curve, you can see that the power curve has a period which is half of the period of the V and I curve. Okay, so you can see that the power curve, the the period is actually reduced by half already. Okay, so that's a characteristic of a power curve, and you can see that this power curve here is always above the x-axis. Why? Because positive always multiply with positive, negative always multiply with negative. So you know positive will be positive answer. If you multiply them, negative you get positive answer as well. That's why our minimum will be 0, our maximum will be V0 I0, as what mentioned here. V0 I0 here will be the maximum if we take sine square omega t to be equals to 1. Okay, so this is our power curve, and if we take an average of this power curve, so if you find the middle point of this curve, you find that it will be middle average at V0 I0 over 2. That's why our average power will be equals to V0 I0 over 2, which if you remember, V0 over square root 2 is VRMS, I0 divided by square root over 2 will be IRMS. Therefore, we can change V0 I0 divided by 2 to be equals to VRMS IRMS. So that's the average power for a pure R circuit. Okay, next we have pure C circuit and pure L circuit. I'll discuss both of these circuit together, and you know why I do so. Okay, again, you take the sinusoidally varying voltage across the capacitor, multiply with the current flowing through the capacitor. We know that for capacitor, it's not the V and the I are not in phase. So one of them is negative cos graph, one of them is sine graph. You can see why is it negative cos. You can see it from the derivation in lecture. Okay, so if you multiply them, you will get V0 I0 negative cos omega t sine omega t. Okay, but never mind. Let's just straight away look at the graph and see the blue curve is again current, the red curve is again the voltage. You see here, the peak of the current will be multiplying by 0 of the voltage. When the blue curve is at its peak, the red curve will be at 0. So the peak for the current actually translates to a 0 for the power curve. Okay, for the power curve, once you reach a peak, you're actually reaching 0 for power because you're multiplying something which is big with 0 for the voltage. It's the same idea also for the peak of the voltage. The peak of the voltage is this peak for this red curve over here. But you see, if you multiply with current at that moment is 0. So you see that the peak for the voltage actually corresponds to the 0 for a power curve. So the peak of the V and the peak of the I should all correspond to 0 at the power curve, which you may observe from this graph over here. Where do you get the peak for your power curve? It's when they are both halfway. Okay, when the I and the V are somewhere in the middle, not the peak, not 0, then that's where you get your peak. Your trough is when the I and the V are opposite sign. Just like V here is negative sign, but I here is positive sign. So you get a negative curve over here for P. Then you can see for the next part, the current is positive, the voltage is positive. Therefore, your power curve for this portion will be positive. So you see that the power curve is slightly different from pure R circuit. For pure C circuit, you have negative power and positive power. And the middle, as you can see, is averaged out at 0. Okay, so the average of the power curve for a pure C circuit is actually 0. It means by you can think of the power at positive range of a power to be gaining energy from the power supply. You can think of the negative part as releasing energy back to the power supply. Okay, but that's not the important part. The important part is you see that they actually average out to 0. so that the average power for pure C circuit is 0. Well, the discussion for pure L circuit is actually similar. For pure L circuit, it's cos omega t times sin omega t, which if you draw the graph here, you see that there are portions where your red and blue are both positive, so you get a positive peak, and there are certain portions where the blue and the red are on opposite side, one positive, one negative, so you get the negative curve. And when the red curve is at its maximum, the blue curve will be at 0. When the blue curve is at its maximum, the red curve will be at 0. So all the peak of V and I will correspond to 0 at the power curve. Okay, the idea is still the same as pure C circuit, so I won't go too much in detail. So again, if you look at this power curve, you know that you average at 0. So the average power for pure L circuit is actually also equals to 0. Okay, so to make a conclusion here, if we see that the V and I are totally in phase, exactly in phase, no phase angle in between them, we'll see that the average power generated will be VRMS, IRMS. Okay, but if we see the current and the voltage to be 90 degree out of phase, 90 degree out of phase, whether leading or lagging, we don't mind about it. But if it's 90 degree out of phase, we'll see that the average power is equals to 0. So if phase angle 0, your P average is VRMS, IRMS. If your phase angle is 90 or negative 90, the average power will be 0. So this is, we can think of it as the maximum average power that you can obtain from the circuit. Okay, then this is the minimum, 0 minimum, then the maximum is P average for pure R. Okay, the idea why I'm saying maximum minimum is because you can see here, our phase angle is 0 and 90, right? But it's actually possible to get phase angle which is not 0 and which is not 90, somewhere in between 0 and 90. It's possible to get this angle if you combine different circuit elements together, like RC or RL or RCL circuit. What you do is combine different circuit elements, then you get phase angle which is between 0 and 90 degree, whether positive or negative. So when you reach that point, you'll be somewhere in between this maximum average power and somewhere in between this minimum average power.